Yeah. So like in normal chemistry, we say organic chemistry is a study of all organic compounds. All organic compounds, that is, those that contain hydrogen and carbon. That is the reason why they are called organic compounds, because they contain hydrogen and carbon. But we have a few exceptions. Not all compounds that contain carbon are called organic compounds. I guess you know that. So in organic chemistry, we're going to look at compounds like aldehydes, ketones, alcohols, thiols, amines, carboxylic acid, amides, a lot of things. Like there are a lot of organic compounds we're going to look at. But for your program, you guys, for summer lessons, I was told to only do approximately maybe like 5, but they're a lot because they also have their own derivatives. So organic chemistry is the study of all organic compounds. Now, these organic compounds may contain hydrogen and carbon, with a few exceptions, of course. You have compounds like an alcohol. An alcohol has carbon and hydrogen and has oxygen. So it's also considered as an organic compound because it contains principally carbon, hydrogen, and oxygen. The oxygen is what gives the compound the alcohol function. I guess you know that. So I defined what organic chemistry is. So for today, it's just an introduction. Then just another highlight. There are those that applied for ENSA, SVT, ENSA medicine, dental medicine, laboratory, and pharmacy. These are the ones that are supposed to attend this course. But if you're interested, you can still attend, as in knowledge is power. But for the ENSA guys, I have a problem because I don't know which schools you guys applied for, because the schools that I know that offer ENSA
Excuse me, sir.
Yeah.
How about APESA?
Yeah, including APESA also. Sorry, I forgot APESA. Yeah, including APESA. Then ENSA, there are some schools that do organic chemistry in their first year. There are some that do in their second year. So I don't know. So what I'm asking from you guys that are ENSA students, or if you know any ENSA student, please tell them that they should confirm with the seniors that they were talking to, so that they know, because other than learning organic chemistry, you might be learning something else. So right now you might be sleeping or doing something else productive, you see. So I don't want a situation where you're attending organic chemistry and you're having organic chemistry in your 3rd year or your 4th year and you're attending it right now. That is not going to be helpful. Yeah. So we continue. So in organic chemistry, you have got two classes of compounds. That is aliphatic and aromatic hydrocarbons. We call them hydrocarbons, organic compounds. So aliphatic hydrocarbons are basically those ones that are straight chains, like a normal straight chain. For example, let me say butane. Butane has got four carbon atoms, and it's an alkane. So you find out that in all aliphatic hydrocarbons, it's basically a straight chain, but with few exceptions, of course. Examples are cyclohexane. Cyclohexane is a cycle. Let me just show you examples. Cyclohexane is this compound here. Now, this is cyclohexane with substituents. You have got the methyl substituent here, and you also have another methyl substituent here. So a substituent comes about when an alkane loses one hydrogen atom. So a methyl is a result formed from methane. Methane is the simplest hydrocarbon that you guys know. I'm pretty sure everyone has done organic chemistry. This is not the first time, isn't it? You guys have done organic chemistry. This is the second time or first time? Second time, exactly. Okay. So methane is the simplest alkane that you guys know. It has got 4 hydrogen atoms and 1 carbon atom. So when you remove 1 hydrogen atom from it, it now forms an alkyl group. So alkyl groups are what you form as substituents in all organic compounds. Yeah, we have got a few exceptions, because when you look at ethers, when you remove a hydrogen atom from it, it now becomes, for example, if it's a methane ether, it becomes a methoxy. So there are those exceptions. But for now, the idea is for all aliphatic hydrocarbons, they are simple chains, just like these ones I've shown you. So you've got dimethyl trisulfide here, the first example. You've got dimethyl tetrasulfide, the second example. So you consider the sulfur carbons the sulfur atoms as carbon atoms as well. As in, we'll look at these rules in the nomenclature. But for now, I'm just giving an introduction, just a perspective of what we're going to do. Then later on, in the next on Tuesday, I'll explain how aliphatic compounds are used and all those things. So you've got the methoxy that I was talking about here. So you have an ether here, then you have an alcohol. So when you remove a hydrogen atom from an ether, it no longer becomes the methyl propyl, it now becomes a methoxy, ethoxy, propoxy, etc. Yeah, so this is a aliphatic hydrocarbons. Then you have aromatic hydrocarbons as well. Now, aromatic hydrocarbons come as a result or are formed as a result of what you call mesomery. So you should take note of that. There's what you call mesomery or renaissance. So when you look at aliphatic hydrocarbons, it's primarily benzene rings. So benzene is, let me say, the backbone of all aromatic hydrocarbons. Now, unfortunately, I won't go as far as explaining how aromaticity and mesomery come about because I'm supposed to go as far as the nomenclature part. So for aromaticity and how aromaticity comes about, I won't do that, but I'll explain how it comes about, just like a bit of an example. Yeah. So primarily, aromatic hydrocarbons are formed from benzene. So you should take note of that. All aromatic hydrocarbons are supposed to have or contain a benzene ring. So a benzene can be represented in two forms or three. The first one is this one with dashes. These dashes here represent double bonds. These ones here, they represent double bonds. Now the circle here shows what I explained or what I called mesomery. So mesomery is basically a state in which a compound, for example, benzene, now because we understand to say that it has got double bonds. Now when you go to, I will give a rappel for the carbon atom, the atomistic part, then later on explain how hybridization is formed. So when you go to the carbon atom, you know the carbon atom is a special atom because you use it for calculating relative atomic masses like you did in atomistic. You use it for a lot of things. So in the same way, the carbon atom here is used for hybridization. Now hybridization here is sp2 because it shares one s orbital and shares two p orbitals. I don't expect you guys to know what p and s orbitals are for now, but just let it be just like a gospel truth or a fact for you. I'll explain about that when we do hybridization. So because the double bond forms an sp orbital of 2, when you look at the fundamental building block of an sp orbital 2, sp2, it forms what you call a pi bond. So the pi bond is the simplest bond that you can ever make in organic chemistry. It's the simplest bond you can ever make in organic chemistry. So because of that, the atom carries out what you call resonance stability. So each atom or each electron here, because you have a carbon atom here and another carbon atom here, they both share what you call resonance. There is one that is being pulled in this direction and one that is being pulled in this direction. But like you know, this compound has what you call a stability that can be interchanged. So it means with its resonance stability, we can move this bond here, and we can move this bond here, and we can move this bond here. So it means when we move all these bonds, when you just, it's still the same compound. When you move this bond here, when you bring it here, when you bring this one here, and you move this one here, the structure has changed, of course. But when you consider like giving it a, what is a dotted array or maybe trajectory, you find that it forms something like a circle. It is for this reason that the benzene molecule in the other representation here, you have a circle. You see, because the bond here can be moved to this position, the other bond can be moved to this position, and the other bond here can also be moved to this position. So when you look at the trajectory that the bonds take because of mesomery, you find that it forms something that looks like a circle. It forms something that looks like a circle. So I have got two examples here of aromatic compounds. You've got this one here, which is an amino acid called methyl alanine, and you also have another aromatic hydrocarbon, which is also called phenylhydrazine. So for you guys that will be doing biochemistry, phenylhydrazine is used to test for what you call glucose molecules or aldehyde glucose molecules. These are aldose. Then for phenylalanine is an aromatic amino acid. So when you test it for hydrolysis, you find that the aromatic part is used to identify its presence in different amino sequences. So there's a question here. Someone says I'm talking too fast. Oh, sorry. So if there are any questions, please, you should tell me, then you ask. So I'll give you guys a rappel for atomistic. I'm told you guys are doing atomistic, and I'm pretty sure you've advanced. So
excuse.
An atom, yeah.
Can you kindly repeat the same aromatic?
Aromaticity. Is it aromaticity or just a aromatic hydrocarbons?
Yes, what you are just from explaining.
So I'll start from here.
Yeah. Aromatic
so
hydrocarbons.
I say in organic, yeah, I'll start from here. I said we have what you call, in organic chemistry, we've got two classes of compounds, isn't it? We have what you call the aliphatic hydrocarbons and the aromatic hydrocarbons. So we say the aliphatic hydrocarbons are primarily those ones at single chains, but with some exceptions. For as long as it is not a ring that is a derivative of the benzene chain or molecule. For as long as it's not a derivative of benzene, it is considered to be an aliphatic hydrocarbon. So I gave two examples here. So the first example that I gave was these ones here, these which are chains. These are just chains. They're just chains. My zigzag, they're just chains. Then I also gave two examples here. This is when you do your nomenclature, you can either start from here or you can start from here. So you say 1, 2. So this is going to be 1, 2 dimethylcyclohexane. Same applies to this one. So you look at which one is the principal chain. So you can start from here. So if this is the principal chain and you've got a substituent here, you're going to name this substituent with another unique type of nomenclature, which I'll look at with you guys later on, but not for today. Today is just an introduction. Yeah, so I said aliphatic hydrocarbons are primarily those ones that are formed from single chains, just like this to my zigzag. I know some of you guys have seen this to my things before. Some, this is the first time. Yeah, just this to my zigzag. So this my zigzag can also mean carbon, like this is oxygen, you have carbon here, you have carbon there, you have carbon here, you have carbon. When you have nomenclature, you can also consider this oxygen as a carbon atom. Yeah, there are exceptions with the rules. It's all about rules. Organic chemistry now is all about rules. So these are what you call aliphatic hydrocarbons. Is that clear? Now we go to aromatic hydrocarbons. So I said aromatic hydrocarbons are built from benzene. So benzene is a molecule or is formed from what you call mesomere. So now mesomere, if I go into details, mesomere, it will take a lot of time. So mesomere is basically in simpler terms, the interchanging or the ability for you to move the bond, this bond here to this position, this bond here to this position, and this bond to this position. That's the simplest definition I can give for mesomere. So if you want more details about mesomere, you can inbox me later after the call. Then I explain what mesomere is. That's if you feel like you want to understand what it is, like what it is in depth. This is the simplest explanation I can give. So mesomere is the ability for you to move this pi bond from this position to this position, and this other pi bond from this position to this position, and this one to this position. Then, like I said, when you take a trajectory of the movement, if you look at the movement of the bonds, it was here and it is here. And then because there will be what you call repulsion and all those things, this bond will automatically have to displace and move to this position. Same applies to this one. There will be repulsion here. When this one moves here, there will be repulsion. So this one has to displace to this position. So you find that there will be an even distribution of the pi bonds. So now, like I said, when you take the trajectory of the bonds, you find out that it looks something like a circle. So that's the reason why benzene can be represented in this form, or you can represent it in this form. In this one is just a plain representation of benzene. Then I said we have got two compounds here. So I said because aromaticity is derived from the benzene atom, it means all carbon atoms or all molecules or all organic compounds that are going to contain a benzene ring will be considered to be aromatic. And I gave two examples. The first example I gave was phenylalanine, which is an amino acid. You guys are going to do, those that are doing medicine will do amino acids in details, but this is just an example. Then there's also another one called phenylhydrazine. It's also going to be done in organic chemistry or in biochemistry. But for now, the idea or the basis or the reason why I've given this is because I want to show you guys where aromaticity is derived from and how it comes about. So aromaticity is a result of this benzene ring. So any compound that you're going to have with a benzene ring, any compound you're going to have with a benzene ring, let it be benzene in this form or benzene in this form, it's the same thing. You are going to call those compounds aromatic compounds. So there's a question here, I think. Yeah, Conrad, you can go ahead.
Actually, you talked about the mesomer as the ability to move this pi bond here to another position. So does it mean that the sigma bonds are unmovable?
No, when it comes to, because you see, the sigma bonds, okay, I like that question, yeah. You've gone ahead of me. So the sigma bonds are a result of what you call hybridization SP. You see, so now the hybridization that we have here is hybridization at sp2, not at sp. At sp, we have what you call two pi bonds and one sigma bond. Now, in this case, we are only considering pi bonds because we are at hybridization sp2. Is that clear?
Yeah, it's clear. Thank you so much.
Yeah, you're welcome. Any other question?
Yes.
Yeah.
According to explanation, we understood. But benzene, does it have for example, if it's in a chemical, if it's in a form?
Okay. I get you. Sorry. Yeah. As in, if you want to represent benzene, so this is what we do. So, like I said, for today, you guys excuse me because I'm just giving an introduction. So we'll go in depth, like explaining this formation of the molecules. But you have a point, what's this, Alicia? So benzene's chemical formula is C6H6. So you count. This is how you count it. You see, at each corner there is a carbon atom. This is how you do it in organic chemistry. When you look at molecules like these ones, at each corner here you've got a carbon atom, and we know and understand that from the aliphatic compounds, every carbon atom in organic chemistry is bonded to at least three or four, but maximum is 4 because we know that the carbon atom has got 4 bonds, you see. Then when we explain hybridization, this is where Codon comes in and says, you've got sigma bonds, you've got pi bonds, and all those things. Yeah, so here, the carbon atom that we're going to have here has got 2 hydrogen atoms. Why? Because there is a carbon here and it is bonded to another carbon. This line here shows a double bond. So we know that the distribution of bonds for a carbon atom is supposed to be 4. So we say carbon here 1, there will be hydrogen on top 2, so there will be 1 there, and there'll be another one in this position. So you automatically have how many? You have 2 hydrogen atoms. Then you have another carbon atom bonded to another carbon atom, and you have this carbon atom with another bond here. So it makes them 4. It makes them 4 bonds. So the same way you come here, you count. So how we do it, this is how we do it. So you count 1, 2, 3, 4, 5, 6. So you have 6 carbon atoms. Then you've got double bonds on each. So this is a hexagon. I think this is a hexagon. So when you count the number of sides, there are 6. But we know that each of them contributes like how many? It's supposed to contribute like 12 hydrogen atoms. Now, because we have a double bond, we're going to divide each of them by 2. So you can do it mathematically, you can count. So if this is carbon here, you've got the first bond 1, the second bond 2, the third bond 3. Then you're going to have 2 hydrogen atoms here on top that are going to bond to this carbon atom here. Let's hope it's clear. Is it clear? So the chemical formula for benzene is C6H6. C6H6. So this is actually the representation here. So you've got 1, 2, 3, 4, 5, 6, and you've got 1, 2, 3, 4, 5, 6. So that's the chemical formula for benzene. Any questions if I proceed? Feel free to ask. I can still go back to the first part. Okay, they're not ready. Huh?
I have a question.
Yeah.
Right. You are saying that this carbon that you have here will be bonded to another two hydrogen atoms. Now you are saying that this line which is inside this benzene atom we have is representing a double bond. Now if we add if we bond this carbon to another two hydrogen atoms, it means that it will have 5 bonds. So I'm kind of confused.
Okay, let me do this. Let me do this. Maybe this would be a bit convenient. Can you see this molecule here? Can you see this molecule here?
Yes.
So this is our benzene molecule. So I said carbon has got 4 bonds maximum. It should never go 5. In organic chemistry, once you put carbon with 5 bonds, it's wrong. Automatically, it's wrong. So we are saying it has got 5 bonds. 4 bonds, sorry, 4 bonds. So this carbon atom here is bonded to how many other carbon atoms? It's bonded to this one and to this one. It's bonded to this one here. Now it's bonded with 2 bonds here. So there's 1, there's 2, there's 3, and there's 4. So we've satisfied this one exactly, isn't it? We come to this one. We also count 1, 2, 3, 4. So this one also has been satisfied. It also has 4 carbon atoms or hydrogen atoms. Oh, sorry, bonds. This one has got 1, 2, 3, 4. This one here has 1, 2, 3, 4. This one here has 1, 2, 3, 4. This one here has 1, 2, 3, 4. This one here also has 1, 2, 3, 4. And this one here also has 1, 2, 3, 4. Is that clear?
Yes, yes.
It's clear now.
Yes,
And
it's
continue.
clear now.
So, okay. So that was about aromaticity and aliphaticity. So now, a rappel on atomistic. So you guys defined, on this one I'll be a bit fast because you guys have already done atomistic. Unless if there are questions. So So you defined an atom. I don't know how you guys define an atom, but an atom is the smallest particle that matter is made up of. Yeah, it can be the smallest in a chemical reaction, but the smallest particle that is built from matter. So evolution of the atom starts from way back with Aristotle, Dalton, J.J. Thomson with the development of the electron, Rutherford with the definition of the atom in the form of the nucleus, and you look at Bohr, Albert Einstein with the definition of the atom in the form of a photon, explaining the photoelectronic effect of the nucleus when it is hit by an amount of energy. Then you go to the development of Bohr explaining what the atom is when you explain it in the three postulates. So you have the first one that explains the absorption of energy, the second one that explains the emission of energy, and the third one that explains the angular momentum of the electron as it moves in its orbital. Then we have the big definition of an atom that we're going to be using, that you guys are going to be using, not as the organic chemists, but you guys that are going to be using in what you call it, atomistic. The definition of an atom in terms of Erwin Schrödinger's definition. This is quantum mechanics. So he defines an atom to be like you guys have said. It's a particle that builds up matter, but he defines the state of an electron to be in what you call a quantum superposition. So you've got what you call quantum superposition, and also what you call quantum entanglement. So quantum superposition is basically the explanation of an electron being in two positions at the same time. Then quantum entanglement is the question. No, as in, don't worry. This is just a rappel. You guys are going to do this in atomistic. Don't worry. I'm just giving a rappel because I have to build this for carbon atom, then later on build organic chemistry. Yeah. So Erwin Schrödinger explains the atom in terms of wave functions. So, like we said, an atom is a building block of matter. Now, Erwin Schrödinger explains the electron displacement in form of two principles. There's what you call quantum superposition and quantum entanglement. So he said quantum superposition is the ability of an electron to be in two positions at the same time, to be superposed, to be one in Rabat, one in Cetat. So that is quantum superposition. But normally, an electron is found in the orbital. The reason why I gave two examples of location at Rabat and Cetat is because that is the kind of arrangement that the electron is found in. Then you have another principle that is quantum entanglement, which explains a factor of displacement. So take, for instance, I'm in Cetat and one is in Rabat. So because electrons are of the same kind, take, for instance, I do, or maybe I hit, or maybe someone slaps me here. Someone slaps me in Cetat. So the person that is in Rabat, because of the principle of quantum superposition, if someone slaps me in Cetat, it means the person in Rabat also gets the same effect. So that is the definition of what quantum entanglement is. So quantum entanglement is an effect that is done on an electron that is superposed. For example, the same idea I gave about I'm in Cetat, another person is in Rabat, and we are electrons. So if someone slaps me or someone beats me, the same effect that has been done to me here in Cetat will be the same effect that will be done to the person in Rabat. There's a question?
Can I bring it back a little bit?
Yeah, there's no problem. Huh?
On the benzene, there I've got a question. When counting,
Okay.
Yeah, when counting the chains that are attached to the benzene, do we start anywhere or there's a specific rule attached to that?
For now, because we've not done nomenclature, you can start from anywhere. But when you do nomenclature, there will be rules where you're supposed to start from. But always, when a benzene ring is attached to, let me see. If a benzene ring is attached to, maybe for example here, it's attached to a methyl alkyl group, it means you're supposed to start from here. If it's here, you're supposed to start from there. You start from where the substituent is. But when we look at nomenclature of the aromatic compounds like benzene, you have what you call the para, meta, and the ortho. So for now, like I don't want you guys to like go into much detail about these things. For now, I'm just going to give you an introduction of how organic chemistry would be like, that you guys should enjoy. Yeah, but for now, don't go too much in depth. You're going too much inside, boss. Yeah, but for now, it's just a plain introduction. Don't worry, a plain introduction. On Tuesday, we start learning properly, like with serious data. For today, I'm just giving an introduction of the core. Yeah. Any questions? So that is it with a rappel. So the quantum entanglement, like I said, is a state of an electron being affected by an external force. So like I gave an example, I'm here in Setat and there's a person in Rabat. Even though they are different, for example, I know you guys, there's Somanza in Setat and there's Somanza in Rabat. An effect done on the Somanza in Setat automatically affects the Somanza in Setat, even though the Somanza in Rabat has no. Take for instance, he's just seated at home and I'm playing soccer in the pitch. Any effect that is done to me in the pitch automatically affects the resource that is seated at home. That is that's the simplest explanation of what quantum entanglement is. Quantum superposition is the ability of two electrons to be in two positions at the same time. So because they are in two positions at the same time, whatever effect is done to one in one position, it automatically affects the other one in the other position. So that is now what we call quantum entanglement. Let's hope it's clear. This is just a rappel of atomistic. You guys have got a clue for atomistic. Yeah. Then now we come to the carbon atom. So like I said, the carbon atom, the carbon atom is a very, very fundamental atom in organic chemistry because it is used for a lot of things. Talk about the macromolecules that you guys know. You've got carbohydrates, you've got fatty acids, lipids, you've got proteins, you've got vitamins, you've got all these things, all these macromolecules. Macromolecules are basically monomer units of these small organic compounds. Now, when you raise them to the power of n, that is now what you call polymerization. When you raise them to the power of n, now they become big. For example, you have ethane. Now, ethane, when the bonds, the double bonds are broken down, it now forms a monomer. So when the monomer is raised to the power of n, when I say raised to the power of n, I mean it's repeated n times. So if it is repeated n times, it now forms what you call a polymer. So now in organic chemistry and biochemistry, we say macromolecules to simply mean these four, is it 3 or 4? The vitamins, the carbohydrates, the, what do you call them? The lipids and the proteins. Or you can go as far as including the nucleic acids for DNA and other things. So when you talk about macromolecules in biochemistry or organic chemistry, in biochemistry, we talk about the nucleic acids, proteins, glucids, which are carbohydrates, and the fatty acids. But in organic chemistry, when you talk about macromolecules, we talk about anything. It depends. You can look about polyesters, you can talk about polyamides, a lot of things we can talk about. But the principle here is the carbon atom will always be the fundamental atom that will be used for bonding, that will be used for any organic compound, like I said in the first place. So now here I explain the principle of hybridization. So this is where now Kondwani comes in with his question, say, now, why is it that the benzene ring only has the pi bond other than the sigma bond? Now, is there any orientation with the sigma bond? So the answer is, because the carbon atom is a special atom. The atom is has the ability for it to be oriented in different positions. So a hybrid is, let me say, a hybrid is another form of anything. For example, you have, say, coronavirus. Coronavirus started from China. Now, these other viruses that we have in Morocco, Zambia, are hybrids of the original virus. Because the original virus, I know maybe might have 2 or more nucleotides that are different from the ones that we have in Morocco, the ones that we have in Zambia, the ones that we have in Italy, all those countries. So what it is that carbon can be in 3 different forms. It can be a hybrid, can be made hybrid in 3 different forms. So the first one is what you call the sp, which forms the 2 pi bonds and 1 sigma bond. Then the other one is what you call the sp2. It forms 1 sigma bond, 1 pi bond And the last one, which is the simplest, the sp3, which forms one single bond, which is one pi bond. So another clarity, the sp forms three bonds. That is what you call alkyls with 3 bonds. Carbon bonded to another carbon with 3 bonds in between. Then you have what you call alkyls, which are ENE. They form 2 bonds. That is two pi bonds. And the last one, which is methane, the one that forms 1 bond, is sp3, which forms 1 pi bond. So the formation of these 3 bonds, 2 bonds, and 1 bond is a result of what you call hybridization. So hybridization is basically the carbon atom has been made or changed into 2 or 3 different forms. The first form is what you call sp. The second form is sp2. The third one is sp3. So depending on the orientation of the orbitals, which is the p and the s orbital, which you guys will do in atomistic, is what you call the s orbital, which is the fundamental orbital. Then you have the p orbital, which is the second one from the s orbital. So the p orbital has got 3 principal orientations. Is what you call the px, the py, and the pz. So depending on which plane you're looking at it's arranged in that order. So you've got the sp, which forms 3 bonds. So you've got compounds that form 3 bonds. I'm pretty sure you guys have seen them. It is a result of hybridization at sp. Now you've got compounds that form sp2, which are compounds that form 2 bonds. Then you've got compounds like a methane, which forms only 1 bond with each independent carbon atom, that forms sp3. It is opposite if you look at it. So you find that sp3 means 1 single bond, sp2 means 2, sp means 3 bonds. Are there any questions at this point?
Kindly repeat what you just explained. I'm a bit behind.
Okay, so I said the carbon atom is a very important atom in the world of organic chemistry, because it is the only atom that can undergo what you call hybridization. So I said hybridization is another form of the carbon atom in say, how can I put it? Like you have this carbon atom. Like let me use the example of coronavirus. So coronavirus was first discovered in China. Now it was discovered in China. Then later on, it mutated into different forms, into other hybrids. So when you're looking for a vaccine, the idea is you're supposed to study the virus that was in China, then later on study the virus that is in, for example, in Morocco. So in one way, it means the virus that is in China and the virus that is in Morocco are different. You see, that's the reason why getting a vaccine is quite difficult, because the virus mutates depending to the conditions that it is exposed to. So in the same way, the carbon atom has got different, how can I put it? It has got different forms in which it appears when it is bonded to certain compounds. Take, for instance, when the carbon atom is bonded to a nitrogen atom, instead of it using the sp3 or sp2, it's going to use the sp bonding, because nitrogen has 3 bonds and carbon has got 4. Now, when you look at effect inductive, which is another topic way ahead, when you look at effect inductive, the idea is the one that has got more bonds is what the carbon atom is going to attach itself to. So the carbon atom will attach the nitrogen atom with 3 bonds. That is sp hybridization, other than using the sp2 or the sp3. So this is the conclusion I gave. So I said hybridization is in how many types? Is in 3 types. The first one, with 3 bonds, it forms 3 bonds. So the first one forms 3 bonds. That is 2 pi bonds and 1 sigma bond. 2 pi bonds and 1 sigma bond. So 2 pi bonds and 1 sigma bond, this gives sp. Then sp2, it gives 2 pi bonds, or let me just say pi bonds, because even though there are c'est la même chose. It's two pi bonds. Then the simplest one, which is sp3, forms what you call a pi bond, a single pi bond. So you've got three types of hybridization. You've got sp, sp2, sp3 in that order. Or if you want, you can go in this order: sp3, sp2, sp. So depending on what order you're going to look at, you take it that way. Then don't worry, like it's noted here. This is a rappel d'atomistique. In atomistic, you are going to learn how these compounds bond, because you're supposed to learn about their cas quantique, their orientation in the way electrons are oriented in the nucleus, or in the orbitals, sorry, in the orbitals, and how hybridization comes about. But I also explain how hybridization comes about with organic compounds. So don't worry, on Tuesday, I'll go in depth. Yeah, so if there are any questions, because even though this is an introduction, I need you guys to understand where certain things are coming from, because we had on Tuesday, we're supposed to, yeah, this is the question here. Yeah, Konwan.
Yes, boss, it's on. We talked about the types of hybridization, that is.
I can't get you, bosses. Your network is cutting.
Yeah, on the types of
I can't get you, bosses. Your network is cutting.
Able to get me now?
A bit. You saying?
On the types of hybridization. The types of hybridization. Yeah. So you said we have three types. That's SP1, SP2, SP3. Now, I'm like on that one.
Yeah.
Is it DSP, something like that? How does it work?
Is it D?
How does it come about?
D.
Yeah. Yes.
The D hybridization.
Yes.
DS.
Yeah, DSP3.
Boss, mind that very badly, boss. No, okay. The idea is, you see, chemistry is a very good subject there. I understand why he's gone all that far. So for now, please, because if I start explaining, I'll confuse your friends and it will cause questions. So after the call, you please come to my DM, then I explain how the SPD comes about. Because you guys, there are some of you that are doing atomistic, there are some of you that are not doing atomistic. So I want to make a level ground for everyone, because if I start explaining the D orientation, because there's also F other than D, there's also F. If I start explaining all those things, I'll confuse the guys that are doing atomistic. So, and I also need the professor for atomistic to also catch up with organic chemistry, with hybridization and all those things. So that when I start teaching, it becomes easy. So bosses, I'm asking from you that at least after the call, please come to my DM, because if I start explaining the D orientation, the hybridization here, I'll confuse a lot of people, and it will cause like a drawback in the code, because I have to really give the foundation. Like, I'm supposed to explain where the atomistic comes about. You see, that's what the problem is. I have to explain the carbon atom, the atomistic, how the carbon atom orients itself, the electrons, all those things, and the shells. So for now, is it okay that we forge ahead? Then I'll explain when you come to my dear.
Yeah, Namizi wakamba.
Yes, sir. At Mr. Lawrence, you're already confused. Yeah, no, you see. Now he's already confused with SP3, SP2, and SP. Now if I go to SD, so it means I'm going to confuse everyone. So I continue. So representation. So we've got what you call form developpé plane, form semi-developpé plane, form compacte, form simplifiée, or bien topologique. So these are the type of representations that we're going to look at in organic chemistry. So you shouldn't be surprised when you look at a molecule that looks like this. You shouldn't be confused, because this is what you guys were using in Zambia. So this one here is an alcohol formed with two carbon atoms. What do you call this molecule? What's the name of this molecule? The one that gets this one correct will get an alert.
Ethanol.
Gets what? Ethanol, exactly. Then this one, yeah, ethanol, and this one.
Butane.
Exactly. Then this one.
Methane.
Methane.
So now what happens to this butane when I put the alcohol at the end, or the oxygen here. What is it called?
Butano.
Butano.
Exactly. So it becomes butanol. So what happens if I put the OH at this position?
Methanol.
Exactly. It forms methanol. Yeah, so that's the simplest alcohol you have. So this is a form Developpée, which you guys have been doing all the way from Zambia. I'm pretty sure you've also done semi-Developpée. Semi-Developpée looks like this. It's the same thing now. You now have alkyl groups. Instead of you branching the hydrogen atoms, you now have the carbon and the hydrogen attached. So this is an example of formule semi-Developpée. Don't be scared of these structures. No, don't be scared. You get used. So this is a type of semi-Developpée. Then you have compact. This one is also known as
question.
condensed. Yeah.
I just want to explain for me the types of bonding you've been talking about, just the pi bonding and the sigma bonding.
No, I don't know about with this type of diagram. I can't really explain how the pi bonds and sigma bond come about, but the general principle is for all double bonds, these double bonds form sp2 and they form pi bonds. So automatically these are pi bonds, these are pi bonds, these are pi bonds, these are pi bonds, these are two pi bonds. Then the single bonds, these are just pi bonds. This is just one pi bond, and these are two pi bonds, two. Then I don't know if I have a molecule with three. Let me check if I have any molecule with three. If I have any, this one here. A molecule with three bonds shows that the first one here, the one at the far end, this one here, this one, it's a pi bond, and the one close to foot is a pi bond. The one on the middle is the sigma bond. So what I advise for you guys to do, those that are doing medicine, I'm pretty sure you guys have not been attending atomistic. You should talk to your friends and ask them when they start doing liaison chimique. Now, liaison chimique is just the background of how the hybridization, the one that Conan was asking about, the D, Shan, how it comes about. But if you want, I can still explain it, but not now because I'll confuse a lot of people. Yeah, so you've got semi-Developpée plane, which is just a build up from this one. But now, instead of you having the carbon atom with three adjacent hydrogen atoms, you have the carbon atom now with only one hydrogen atom, but you're showing how many are bonded to that carbon atom. Example is this one here. You've got this molecule. What do you call this molecule? The one that gets correct.
Methylpropane.
So this is 1, 2, 3. It has got how many atoms? 3 atoms. So it forms a propane, and with a methyl on the second carbon atom. Yeah.
But can you please explain from number 1 again?
From here. From number 1, chapter 1, from organic
No,
chemistry.
here. Yeah, here.
From
No,
here.
here. Formule
Okay.
plane.
Semi-Developpée plane. So the formule Developpée plane is just the normal. It's 1 o'clock. Arrangement of the carbon atoms and the hydrogen atoms in a plane, as in on a plain paper, for example. So, for example, you have what do you call this molecule? I forgot it. So you've got you said butyl. I forgot it. So you've got 2 carbon atoms. So 2 carbon atoms forms what is it? Ethanol. So this is going to be ethanol. So ethanol in a plane, you write it carbon 1. We take a bond dash, carbon 2, then with respecting the rule that states you're supposed to have at least 4 hydrogen atoms bonded to the carbon atom. So here you've got 1, here you've got 2, you've got 3, and you've got the 4th one there. Same applies to this one. You've got 1 here, 2, 3, and 4. Then with a semi-Developpée, there's another one. There's what you call the semi-Developpée. You sometimes adjust. You can break this hydrogen here, and you have oxygen bonded food called hydrogen, like that. So same applies to butane. So butane is CH4, H2N plus 2. So CH4, that's how many hydrogens? So 1, 2, 3, 4, 5. So 4, 5, 6, 7, 8, 9, 10. So CH4, H10. So when you are going to write a formula Developpée plane, you're going to like first write the carbon atoms. The principle is first you write the carbon atoms. Say 1, 2, 3, 4. Then you bond each of them like that. You bond. So if you say 1, 2, 3, 4, you bond them like that. Pa, pa, pa. Then you respect the rule that states that each carbon atom is supposed to have 4 bonds. So you go there with 1, 2, 3. So this forms a methyl alkyl group. This one forms H2. Unfortunately, don't have a name for H2 compounds. Yeah. So this one forms H2. This one also forms H2. So the carbon bonded to 2 hydrogen atoms to other 2 adjacent carbon atoms. Same applies to this one. So you have got hydrogen, hydrogen, and hydrogen there. So this whole compound respects the rule that states that a carbon atom is supposed to have au moins 4 liaisons. Is it clear?
Yes.
It's clear. Same applies to methane. So this is the semi-Developpée plane. It's just a build-up from the same. So if we want to give a semi-Developpée for this one, we'll say 1, 2, 3. There are 3 hydrogen atoms. So we're going to say H3. Let's hope you guys like in this organic chemistry I'm doing. It's just the normal chemistry that you guys have done before, but now with a bit of new details and the French and other things. I hope you guys know how to write chemical formulas. Like you understand when I say H3, it means this carbon atom is bonded to 3 other hydrogen atoms. So that's where the semi-Developpée plane comes from. So you've got a carbon atom here. Where's the mass? A carbon atom here bonded to 3 hydrogen atoms. So you're going to say CH3. So it's going to be H3. Then here in the middle with another tire, which is here. This is an example. Yeah, something like this. Normalement, if we were to use the formula Developpée plane, not semi-Developpée, but Developpée plane, it would be this carbon atom bonded to 1 hydrogen there, 1 hydrogen there, the other one here, and the other one here. Now, this is semi-Developpée. It's, what does semi mean? Like, it's a bit advanced from the previous one. So you have, instead of you writing independent hydrogen atoms, you are going to write just the number of atoms that are bonded to this independent carbon atom. Same applies to this one on the middle, because like I said, in organic chemistry, you're supposed to obey the rule that states that a carbon atom will always bond to 4 other carbon atoms. 4 other carbon atoms. When you explain the mechanism reactionnel, there we now see why certain compounds are formed because of certain principles. Now, I won't go as far as that, but it's just a background information that you guys are supposed to note. Yeah, so carbon here forms 4 bonds. So automatically with a 3 plus this 1, it forms 4. Same applies to this one here. This is carbon 1, 2, 3. And the hydrogen here. Normally, if we're to use the formula Developpée plane, we're supposed to write the hydrogen on top. Now we're using the formula semi-Developpée plane. So the hydrogen, we can bring it here. We're just showing there's 1 atom of hydrogen that is being bonded to this carbon atom. Is this part clear? No, don't look, this is just examples of how these molecules can be written in the semi-Developpée. Don't be scared of these atoms and the zigzag thingy. No, don't be scared. Yeah. Any questions so far? Okay, I'll take silence to be questions. So we proceed. Then you have got formule compacte. Formule compacte can also be called formule condensed. It's condensed. It's you see, if you've noticed something, these are just build-ups from formule Developpée, Formule Semi-Developpée. Now we're going to look at Formule Compacte. So Formule Compacte is here's an example. Here, what molecule is this? Those that have done organic chemistry, what molecule is this? The second one. What molecule is this? Or maybe what's the principal function here?
The carboxylic acid.
No, it's not a carboxylic acid. It's an alcohol.
Oh, something like
so,
ketone.
Someone says that it's a
like it has got a ketone group, if I'm not mistaken.
Yeah, no, it's actually it has an aldehyde group, not a ketone group.
Aldehyde. Okay.
Aldehyde. So the ketone comes in the second place. So guys, don't confuse the people. So yeah, so this is an alcohol. So the alcohol has preference when you compare it to the aldehyde. So the principal function for this molecule is the alcohol. So yeah, we'll talk about that later on when you do nomenclature. But for now, this is formule semi-developpé plain. Now, when you bring this formule semi-developpé to condensed, now condensed, we just look at how many atoms are bonded to these atoms like carbon, hydrogen, and others. Now we just cancel the bonds. We just cancel these bonds and we have our molecule. So the CH3 here, CH3 comes as CH3. Now the carbon atom here is bonded to hydrogen and chlorine. So when you are doing the condensed, you can either write the chlorine here, but not here, in front of the carbon atom, either just after the carbon atom, or maybe after the other atom that's bonded to the carbon atom. Not this side. If you put the chlorine here, it shows that the chlorine is not bonded to this guy, it's bonded to the methyl group. So the principle here is when you're writing a condensed chemical formula, like this one here, you are supposed to first look at which atoms are bonded to which atom. So which carbon atom is bonding to which other atom other than carbon. So here we have a CH that is being bonded to a chlorine atom. So when you're writing a condensed chemical formula for this molecule, we're going to say CH plus the chlorine. Like I said, the molecule that's or the atom that's being bonded, the adjacent one, should always be after the carbon atom, or should never be before the carbon atom, but should be either a côté or should be after the atom that is bonded to carbon, like another atom that's bonded to carbon. In this case, we have hydrogen. Same applies to this one here. So you have CH. So if you write this OH here, it's wrong. You're supposed to write it here because it's this CH that's bonding to this one. It's this CH that's bonding to this one. Now, some of you might have questions, might ask me this question, which is a very good question. You might say, okay, Daliso, you see, there's CH here and there's also CH here. Normally, in chemistry, if we were to say CH and close bracket and put the 2 below, would that be wrong? No, my answer would be, for as long as you've given this molecule here, you've shown me that this is the molecule you're looking or talking about, then you give me CH2 with everything in parentheses, then you put the chlorine and the CH. I will say it's correct because I know you're saying, okay, there's this part here that's bonding to this thingy and there's this part here that's bonding to the hydroxyl function. But with other people that do not understand the principle of like where you use the brackets and the index below, it might be wrong because they feel when you're writing these chemical formulas and you put a 2 here, when you put a 2 below and say CH2, it might mean the CH here is appearing twice and is bonded to each other, like the way it is here, it's bonded. Then when you have the chlorine and the hydroxyl, it would mean the chlorine and the hydroxyl also have a bond to themselves, you see. So what I'm trying to say is, for me, when you give me a molecule like this, you give me a background information about the molecule. You give me that this is the molecule I'm talking about, and this is its condensed chemical formula. I will take that, I'll consider that. But for a person that does not understand a person that does not understand the orientation of semi-developed plane to Formule Compacte, please write the molecules as they appear. So CH bonded to chlorine, CH is bonded to the hydroxy function, then the aldehyde function here, the carbonyl function, remains at the end. So with a with a formule Formule Compacte, with the Formule Compacte, you are never supposed to show the bonds, even if it forms 3 bonds. Even if it forms 3 bonds, you are not supposed to show the bonds because it's compact. I'll take you back to the introduction here. You see, there are these molecules that when you guys do your practicals in organic chemistry. So when you look at this molecule here, I don't know what molecule it is, but the idea I want to just bring or draw from this is, when it's compact, you don't have these lines. You don't have these lines. This is what you call a ball and stick model of organic compounds. So in the compact structure, this white atom is close, it's connected, it's compact, like they are together. That's the reason why you are not supposed to show the bonds. But a person that understands that an aldehyde forms a double bond on the oxygen atom will say, no, this is correct. You see, because they understand that the function aldehyde forms a double bond on the principal carbon atom. So are there any questions before we continue with the condensed chemical formula? So basically the condensed chemical formula is just like this one. This is semi-developed. Now you efface, you remove all these bonds, because with the formula compact, it's compact. That's the reason why we don't have bonds. You have the CH bonded to another CH2, you have the CH2 bonded to another CH2, you have the CH3 bonded to another CH3. Like, it's compact, there are no bonds. Let it be 3 bonds, 4 bonds. No, there are not 4 bonds, but if there are 3 bonds, if there are 2 bonds in the structure compact, you're not supposed to show the bonds. Then here is just an example of an amino acid. Let me just say a protein, because these are independent amino acids. You've got glutamate, lysine, and cysteine, and glycine. So this formula here you are seeing is a formula semi-developed, not compact. It's a formula semi-developed. Now, if this formula semi-developed was written in a Formule Compacte, we'd write it in this way. It would say, okay, you have a carboxylic function in this place. So the carboxylic function can either be written in 2 forms. You can write it as H or C, or you can write it as C or H. So like the rules of mathematics, they also apply in organic chemistry. If you have got two similar atoms like oxygen, you're allowed to write CO2 in this and H. It will show that there are 2 oxygen atoms that are formed in the bond in the function carboxylic. So same applies to this other part here, the CH. So if we're to write a function compact, it would be CH, NH2, CH2, CH2, CO, NH, HC. Then you bring this one, so you'll be like CH2, HS, CO, NH, CH2, CO2 subscript 2, or COOH. So I'll repeat. So you can write this as HOOC, or you can write it as where's the mouse? You can write as CO2 subscript H, CHNH2, CH2, CH2, CO, NH, HC, C2, HS, CO, NH, CH2, CO2H. Now, the chemical formula, when we write it, it'd be like carbon, hydrogen, carbon, hydrogen, nitrogen, carbon, hydrogen, nitrogen. But for as long as someone understands what you're talking about, they understand. If you tell them that this is a protein with 3 different amino acids, you've got glutamate, cysteine, and glycine, they will follow, and they'll be able to understand what's happening. Are there any questions so far? Mr. Elisha, you can come in then, Taonga.
Yeah, I don't know if you study the chapter, but on the long one, each studies with the 3 different amino acids, the 3 different stuffs.
What's the problem?
Okay, Taonga come in. I'll ask it. Let me formulate my question.
Okay. Okay, can come in. What's the question?
I wanted to find out if like there's a CH.
This one?
Yes. Is it possible for us to summarize now the second molecule CH2CH? No, on the glutamate.
See this one? Glutamate.
No.
Yes.
Yeah.
You can say it's CH2 parentheses 2 subscript. Is it okay?
Yes, that's okay. Thank you.
Yeah, that was your question, eh? Yeah, so as in you can make it as simple as possible if you want. You can make it as simple as possible. So you can say, I'll repeat this, Elisha. So if this was compact or condensed, the formula would be HOOC. Then I say it can also be written as C, because you know the function carboxylic is COOH. The carbon bonded to oxygen and the carbon bonded to the hydroxy, which is this thing here. So it can be written as hydrogen, oxygen, oxygen, carbon. So HOOC. Or you can write it as CO2H. Or you can write it as COOH, CHNH2, CH2, parentheses, 2 subscript, to show that there are 2 of these. Or if you want, you can continue with the CH2, CH2, CONH, HC, CH2, HS, HS. Because another thing, if you change attention, if you change and you put the bond on the hydrogen atom, if you change this, if the hydrogen is in front, it now means something else. So please, you guys that be doing organic or biochemistry, please take note of which atom is bonded to which atom and how the functions are written. Because if you if you write SH, it no longer becomes what's this? A cysteine molecule. I don't know what it becomes, but it now becomes a thio. It's a derivative of the alcohol. It's also called a sulfur hydride. So if you change and put hydrogen, it no longer becomes what's this? What do you call this molecule? It no longer becomes a cysteine molecule. It now becomes something else. I don't want to go into biochemistry. I will confuse everyone. So it becomes HC, CH2, HS, not HS, not SH. Please, it's HS. If you put SH, it now shows that this molecule has got 2 functions: the carboxyl or the amide here, and a thio. So it now becomes something different from this one. Then you continue, it becomes NH, CH2, CO2H, ou bien COOH. Any questions? So the simplest one we can use is this one. Like I said, you have CH3, CH2, CH2, CH3. Now you just move these bonds. Pa, pa, pa. So like Taonga asked, so other than writing this whole thing, we can say CH3, CH2 on parentheses, subscript 2. But don't say this is wrong. Don't say CH2, you close open parentheses and put 2, and say open parentheses, close parentheses. Like you just make CH3 2, CH2 parentheses 2. No, that is unacceptable. You're defying the rules of organic chemistry. So any question? So we forge ahead. Then there's this one. Topologique. I feel you guys have seen this before. Yeah, so topologique is basically the zigzags you guys maybe have heard, have seen before. Yeah. So with formula simplify, this one is simplified. So any compound that you want to write in organic chemistry, if you're very fast, if you are very fast and you want someone to really understand what you're talking about, you just drink a zigzag like quack, 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 quack. So if you don't take a zigzag without this one, right, for now, let's forget about this line on top. I draw this zigzag 1, 2, 3, 4. So this compound, it's a compound actually. It's a compound. So how we name it or know that this is a compound is with this principle. So we understand to say that each adjacent or maybe each ending, each pointier or bien a point that is has a climax and has got a down max. So it's a carbon atom. So you've got carbon here, you've got carbon there, you've got carbon there, you've got carbon here, and you've got carbon at the end. So each climax, each what do you call this point? Like the down part, the pointy parts, all the pointy parts have carbon atoms, including the far ends. So this one here has got the carbon atom there. Now the carbon atom, like you guys know, they will never show you with the Formule Simplifée or bien Topologique, they will never show you that this carbon atom is bonded to hydrogen. It's you to write the hydrogen atoms. So if that is understood, this is a molecule that contains how many carbon atoms? You've got 1, 2, 3, 4, 5. If it has got 5 carbon atoms, it means it is attached to three independent hydrogen atoms here. Now I said we should forget about this thing on the middle here for now. We should just forget about it. You have got another one here, that carbon atom. Then it's bonded to this carbon and also bonded to this one. So it means there is one hydrogen this side and one below. So this one here in the middle will now have how many? 2. So it's going to be CH2. Now same applies to this one. There's a carbon atom here. There's one that's bonded to this one, and there's another one bonded to this one. And there's another one, the invisible ones that you guys cannot see. There's one there. There's one there. There's one there. There's one there, and there's one there. So it now forms 1, 2, 3, and 4. So it shows that the carbon atom here is bonded to 2 carbon atoms. There's this one that is here, and this one that's there. Then it's also bonded to 2 hydrogen atoms that are there. Always, when you're seeing something like this, know that this is a compound. This is a compound with carbon atoms. Now the hydrogens are not shown. That's why it's called Simplifée. Like it's simplified. It's the simplest formula that you guys can have. Yeah. So now if we're to name this molecule, now with the principles of nomenclature, so we're going to consider the longest chain, and we're going to look at the substituent where it is, then we're going to name it. But for now, we're not looking at nomenclature. We'll look at nomenclature later on. But that's the idea. The idea is when you see something like a zigzag, here I have examples. When you see something like a zigzag, which one am I going to use? This one. Here, this zigzag thing here. It shows that here you've got the carbon atom bonded to hydrogen, 3 hydrogen atoms. So this carbon has got 3 hydrogens that are going to be bonded to it. So 1, 2, 3, plus this carbon here, because this carbon is also bonded to this one here. So it forms 4 bonds. Same applies to this one. This one here has got already 2 carbons that are being bonded to it. There's this one here and that one there. So you've got 1 hydrogen, another hydrogen. So the hydrogens, you can write them in any way, any fashion. If you want, you can write them below. if you want, you can write them on top. But when you talk about stoichiometry, now this is where things become a little bit demanding with the position of the hydrogen atom. Either it's in front, if it's behind, like you're supposed to really pay attention to those ones. Yeah. So with the formule topologique ou bien simplifié, it's just to my zigzag, like this one here. So you have carbon with hydrogen, carbon here with this methyl group. And the methyl, we know that it has got the carbon below, and it has got hydrogen. Then you come here, this is a carbon again. This carbon is bonded to this carbon, and it's also bonded to this other carbon here. So you have this carbon with how many bonds? With 1, 2, and 3. So it means this one will just have 1 hydrogen, other than 3. It will just have 1 hydrogen. So this is the formule simplifié topologique or bien topologique. Are there any questions with the formula zigzag? It's also called formula zigzag.
On B, there where we have one which is on top. Is there on top also a carbon, or maybe
this one?
There's hydrogen. Yeah.
This one?
No.
Where? This one?
Wait.
Or behind this previous page?
B. No, the same one where you are B. Pay up a in mouse, just move right a bit. Oh la la.
B.
Yeah.
No, as in, tell me, is this part? Is it
no,
this part?
In fact, C. No, not
C.
B. That's all. C.
C.
Yeah.
C.
The second C.
Yeah.
Apple where we have come
nitrogen
to the far end, the far end.
This one.
No.
This one.
On top.
This one.
So pair
this
on
one.
top. No. Where you were? The other one
hey.
On top. No.
Hey.
The opposite. Yeah. Yeah. Where you were?
This side.
Yeah.
On top. Yeah.
Does it mean that there's also a
it means that at the far end. Yeah, please take note, guys. At the far ends, at each far end, you have a methyl. When you're writing these chemical formulas, when you get used, you'll be just writing methyl here. At the far end of a carbon atom, and this carbon atom is bonded to 3 other hydrogen atoms. Same applies to this one, 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 this one there, this one here, 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 there. Like for as long as it's at the far end, it's a methyl group. But if it's not at the far end, when it's in between, like here, for example, here, you have this carbon atom, and this carbon atom is bonded to this one here, and it's also bonded to this other one here. So it means this one has already satisfied 2 bonds. There's this bond and this bond. So there are 2 more bonds that are supposed to be. There are 2 more bonds that we're supposed to add. There's this hydrogen here and this other hydrogen here. Is it clear? So at the far end, please, at the far end, take. Then for double bonds, it's the same principle. We know that the double bond is a bond plus. So for this carbon atom that we have here, so it is 1. It already has 1, this side 1, already has 1, 2, there's this one 3, and there's this other one here below, the other pi bond. It forms 4. So this one here does not have any hydrogen atoms. It only has carbon atoms attached to each other. So you have this carbon atom bonded to this other one here, bonded to another one here, and bonded to another one there. So because of the double bonds, we know that the carbon atom is supposed to occupy 4 bonds, or supposed to have 4 bonds. So it won't affect anything. You won't have any hydrogen atoms here. You only have the hydrogen, or the carbon, and the carbon there. So at each far end, or the extreme far ends, you are always going to have a methyl group. We are going to have a methyl group. A methyl, not methane, a methyl. A methane with 1 hydrogen atom less. So when a methane or an alkane loses 1 hydrogen atom, it now becomes an alkyl group. it's not only methane. You have got propane, you've got ethane, you've got butane, butyl. Butane becomes butyl. You've got hexane, which becomes hexyl. Pentane becomes pentyl. What's this? Icosa becomes icosyl. Icosa means you've got 20 carbon atoms. So it becomes icosyl. You just put the il at the end. Is it clear for now? Is it clear? The topology, not the nomenclature, the topology.
I've got a question.
Yeah.
Can you please repeat what you mean, like the difference when it's a double bond, why there are no hydrogen atom?
I'll use this. You look at this. You see this molecule? You can see it. Yeah. So
yes, I can see.
This one here, how many bonds are being shared between this carbon atom and this one here? There are two, isn't it?
Yes.
So, and the principle is the carbon atom is supposed to have how many maximum? 4.
Yes.
So this is what we do. So we have a carbon bonded to this carbon here. So we are considering this one, eh? This one. We're considering this one. You have this carbon here bonded to this one. Shinga, how many? 1, 2,
1, 2, yeah.
And here we've got how many? 1,
1.
And here we've got how many? The other one, the fourth one. Now, what happens to that other molecule is instead of you, au lieu de having hydrogen, you have a carbon atom. You have a carbon atom.
Oh,
you see what? Yeah. Instead of you having a hydrogen, you have a carbon atom. This is what is happening here. Instead of you having a, what's this? For this one, instead of you having a hydrogen here, you have another carbon atom at the far end. So it means this carbon atom has the first bond, the second bond, the third one, and the fourth one, this one.
Okay.
Now the fourth one is shared between 2 other carbon atoms. There's this other one foot. This one foot already has 1. There's this 1, there's this 2, there's this 3 here. So it means this one below will need the hydrogen atom because it does not satisfy the rule. The rule is we're supposed to have 1, 2, 3. Oh, actually it does satisfy.
Isn't there bromine already?
Yeah, it does satisfy the rule. Sorry, it does satisfy the rule. So we have bromide already there. So you have 1, 2, 3, and 4. Ça va?
Okay. Merci.
Any questions? The ladies, you're not asking questions. It's clear. We continue. So for Developpée. So now we'll get to the most interesting part. The règle de nomenclature.
Sorry, Dalisa.
Yeah.
Sorry, Dalisa. I have a question.
Yeah.
Can you explain C again?
C.
The part where there's like 2 double bonds.
Nitrogen.
I don't understand.
The part where there are 2 double bonds.
No, down. C.
Okay. No, as in I want to use this one. I want you to first understand this one, and we'll look at that one later. So we are saying the rule is the carbon atom is always supposed to occupy or have 4 bonds. Steph? It's supposed to have 4 bonds.
Yes.
Now, if it's supposed to have 4 bonds, it means we have this carbon atom bonded to 1, 2. So automatically we have how many bonds? We're looking at this carbon atom here. It has got how many? 1, 2. I'm asking, it has got how many? 2, isn't it?
Yes.
So it has got 2 this side. Now, when you go on the other side, we're still on this carbon atom. How many does it have? It has another one. So how many are there together? There are 1, 2, 3.
Yes.
Yes. Then we have the last one here, the fourth one. Then with the fourth one. Now, because the molecule that we are looking at in the other example does not have a hydrogen. It has this carbon bonded to another carbon atom here. You see, the reason why we're not adding the hydrogen atom is because it has already satisfied the rule which says that the carbon atom is supposed to occupy at least 4 bonds. That's the least it's supposed to go, 4 bonds. Nothing much, nothing less. So we have 1, 2, 3, and the fourth one. Now the fourth one, instead of it bonding to hydrogen, it's bonded to a carbon atom. So the carbon atom now continues. Sava. Is it clear?
So on C there where there are 3 lines.
Which one? This one?
Down. No, down. The next question. There. Yes. Down.
This one? This one?
Yes. Those 3 lines.
So where there are 3 lines, you have 1 carbon here and bonded to, so there's this carbon here. There's another one. Now, the way in the way we represent this one, there's another carbon atom here actually. There's another carbon atom here. Now, because it forms sp or hybridization. So it means the geometrical rotation of the compound is 180 degrees. So the geometrical orientation of the compound is 180 degrees. So it forms a plane, like it's straight. So there's another carbon atom here. There's another one here. So there's this carbon atom, and there's another one here. So this one here is what is forming these 3 bonds. So if there's a carbon atom here, it means there's this other one. There's this other bond.
Yes.
So there's one from this carbon here. There's one from this carbon. I think I have to enlarge this because I'm pretty sure everyone will ask me questions that far. Can you guys see?
Yes.
So there is 1 carbon atom here, one here. There's another one here. Same applies to this other side. There's another one here before coming to this one. So this carbon atom here is the one that is contributing to these bonds. And there's another one here, it's also contributing to these bonds. So this one here already has 1 bond. So this bond plus these 3 from this carbon atom here, that's there, gives how many? Gives 4. N'est-ce pas? Isn't it?
Yes.
It gives 4. So same applies to this other carbon atom that we have here. We have 1 carbon atom that's there and another one that's here. So this one contributes 1 bond to this other carbon atom. Now, when you look at these ones here, so if you add this carbon atom's bond to these ones, how many are you going to get? You're going to get 4. So the principle always is in organic chemistry is you are supposed to occupy or supposed to have 4 bonds. Anything, even in your exams, when you're writing your molecules, when you surpass 4, just know that what you're writing is wrong. Please take note.
That okay, I don't.
No, ask.
I don't know how to point out the carbon for you, but that first one that you're pointing at, is it that there's like a hydrogen connected to it? Because for me, I'm counting only 3 bonds. So is it that there's a hydrogen that we can't indicate?
Yeah. There's actually. Let me create a page, so that maybe I can explain how these things come about. Draw. So you have this line 10. This is a molecule. I'll just give a simple then the molecule goes like that. Then you have a chlorine, maybe here, the chlorine like that. So what I'm saying is you have a carbon atom there. You have another carbon atom here. You have another one there. You have this one here. And you have the chlorine there. So it means this one bonds to 3 different hydrogen atoms. 3 different hydrogen atoms. Then this one, it does not bond to anything because you have this one, the first bond 1, the second bond, which is the sigma bond 2, the other pi bond 3, and the last pi bond 4. So automatically, this carbon atom here has already satisfied the rule that states that each carbon atom is supposed to have au moins 4 liaisons. Same applies. So what is done here, because this is symmetry, what is done here is also done on the other side. So this carbon atom has 3 bonds already here. This sigma, the pi, and the pi. Then you have another one that's bonding to this other carbon atom, this side. So now with this one, it has got hydrogen, okay? Now hydrogen, because we have 1, we have 2, plus the missing ones, hydrogen. Sorry guys, I'm using hydrogen. Let's hope it's clear. Hydrogen.
Yes, it's clear now.
It's now clear for everyone. So we continue. Because I have a lot of things to explain about nomenclature. Is it clear for everyone?
Yeah, it's clear.
There's a question? If there's a question, please ask.
Yeah.
Ask. What's the question?
Just from
What's the question?
yeah, I want to ask you where that's coming from.
I can't get you. I can't get you.
I hope anyone should draw a big man. Open the box.
Yes.
There.
You have a question there?
Yeah.
Here. What's the question?
No.
I should re-explain.
No.
I'll explain. Don't worry, I'll explain. The idea is, you see, not to just get things by heart. No, you're supposed to understand why it's there, you see. So I'll re-explain. No worries. I'll explain. So this is a molecule we have. So we'll change it. We'll give it something like that. Then we'll give what compound? We'll put chlorine here. We'll put what are we going to put here? We're going to put bromide. If we want here, we can put another atom. We say we'll put
N.
We put what?
N.
What's N? Nitrogen.
Oui.
Bosses. No, we'll put
hydroxide. We'll put hydroxide.
Beta, boss. Beta. Yes, not N. N will bring issues here. I want to make this as simple as possible. Yeah. So we are saying, so there's a carbon here. This is where the problem is. There's a carbon there. There's a carbon there. There's another carbon here. So the diagrams are drawn to scale. There's another carbon here. So the principle, this is just this part here. It's just an addition. This should not confuse you. We're just giving this molecule some more detail. But this is the most important part that you guys are worrying about. So we are saying there is this line here now with triple lines. So the first one here, there's a carbon atom, there's a carbon atom, and it is bonded. We said at all the far ends, you always have a methyl, and the methyl is hydrogen, 3 hydrogens with 1 carbon. So you have hydrogen there, hydrogen here, and hydrogen there. N'est-ce pas? Now, this carbon is bonded to another carbon here. Now that you can see, like I said, the sp forms what you call a geometrical orientation of 180 degrees in 3 dimensions. in 3 dimensions. So in 3 dimensions, the sp, the carbon atom, forms a hybrid of sp, and the geometric orientation of that orbital, the sp, it's 180 degrees. What is 180 degrees? 180 degrees, take a line like that, sorry. Then 108. So with 180 degrees, we don't know exactly what the other part looks like, but we just know that it's a straight line. It's a straight line. So with a straight line, you never know. Maybe there is a carbon atom here, there's a cation, but this is the principle. So with 180 degrees carbon, the molecule like that, you have one carbon atom that's there. Now you can see it, and there's another one that's there, and there's this other one here. So we are saying the carbon atom is always supposed to, like, you are supposed to put this back here. The carbon atom always has 4 bonds, four. You never surpass 4. It will have 4 bonds. If you, like I said, if you put 5 bonds, if you put in an exam and you put 5 bonds, just know that that question, if you're putting 5 bonds, you've already got it wrong. If it's 5 marks, you've already lost 5 marks. Never should you put 5 bonds on a carbon atom. Never, jamais. Even if you feel you are a master in organic chemistry, wafikapo, no, 5 bonds, never. Because with when you explain how 5 bonds comes about, now you're supposed to use a reaction mechanism. Now with reaction mechanism, this is where now we explain now the 5 bonds and how the 5 bonds now become 4 bonds. Like never, you're never supposed to put 5 bonds, never. It's always 4 bonds. If you write an exam, like I said, and you put 5 bonds, just know that that question, it's wrong. So always the carbon atom is supposed to have 4 bonds, 4. So this carbon atom has 4. There's this one that's bonding to this one. So there's this bond here. So we'll say 1. There's this one here, 2. There's this one here, 3. There's this one here, 4. Now, this carbon atom here has other bonds for it. There's this first pi bond, second pi bond, the third, which is the sigma bond. So automatically now we have 3. Now there's this other one here, because this carbon atom is not bonded to hydrogen, it's bonded to another carbon atom. So there's this other bond here, this one with sp3 sp3, because sp3 is the only one that forms a single bond. So the sp hybridization is here. Please take no time, because I know some of you start asking me, no, sp. So the sp hybridization is only here where you have the 3 bonds. Where you have single bonds, it's sp3. Where you have triple bonds, it's sp. Where you have double liaison, it's sp2. Please take note, because questions will be asked. Now, to simplify your life, because we'll be telling you to calculate if it's sp3 or sp2. Now, if you just look at the molecule and look at the bonds that you have there, if the bonds are double bonds, you just write sp2. If it's a single bond, you just write sp3. If it's a triple liaison, it's sp. It's the simplest, because they will ask you to calculate. But if you just have that principle in your head, if you just have that principle saying that every time you have a single liaison, it's sp3, a double liaison, sp2, triple liaison, sp. Nisha, we've already the exam. There's no problem. Is there any question before we proceed? I must be concluding. So there are no questions. So I sum up once again. So
there's a question.
May
we go back to the previous slide? Yes. I need to ask. Oh, not.
Yeah. The one I was drawing. This one.
No, not the one you're drawing. The other one is
this one.
Yes. Just to be clear, at the end, like at the end of each diagram, Is it always that there'll be hydrogen atoms or molecules or also carbon?
Yeah, as in if it's drawn like this, it means there is a hydrogen. But if there's another molecule that's included, for example, an alcohol, just like this one, if you have an alcohol here, OH hydroxyl function, it does not mean that you have a carbon there. It means you have an alcohol. This is now what brings me to this part, the nomenclature part. So, like I said, in organic chemistry, we have got a lot of organic compounds. Take it carboxylic acid, esters, amides, nitrites, aldehydes, ketones, alcohols, thiols, amines, ethers, alkenes, alkyls, substituent, halogens, and alkanes. All these, whenever you have a molecule, like the one that you just from telling me, this same one, you have hydrogen carbon at the far end. Now, if you change and put another atom here, for example, you put hydrogen bonded to oxygen. Now this whole thing changes. It no longer becomes an alkane, because this is an alkane, but again with an alkyl group here with a triple bond. So we'll look at nomenclature and I explain how you write the name of these things. Yeah, but the principal function here, if you put the alcohol, now this becomes an alcohol with a chlorine atom with a triple liaison. So if the if the alcohol function of the hydroxyl function is at the far end, it now cancels out the rule that states that you're supposed to have a methyl group at the end. So if you're going to have OH here, OH, and you have nothing here, it means here would it be CH3? It's just carbon bonded to oxygen bonded to hydrogen. With this one here, you have a CH3 because you have nothing bonded to the carbon atom. You just have hydrogen atom. You just have hydrogen atoms. There's this one there. There's another one. Like the imaginary, you draw them. Yeah. So is the question been answered, or I re-explain?
Yes, it has. Thank you.
All right. So now we got for now this part. I'll be a little bit fast because you guys at 14 hours are supposed to prepare for your next class at 15. So like I said, now with the rules of nomenclature, the International Union of Pure and Applied Chemists has got ways in which we name these organic compounds. So you find sometimes names like aspirin. Aspirin is a nom usual. It's a name that is used most of the time. But the International Union of Pure and Applied Chemistry has got a name that they give for molecules like aspirin. Not only aspirin, there are a lot of molecules. So when you go to the International Union of Pure and Applied Chemistry and say, I'm looking for aspirin, they'll ask you, what are you looking for? I say aspirin. They'll be like, we don't understand you. So the idea of nomenclature is to bring all chemists from all different parts of the world to one common understanding, to understand what molecule someone is talking about. So if I say, give me salaric acid. So if I'm working on the International Union of Pure and Applied Chemistry, I understand that salaric acid is aspirin, but its common name is aspirin, but its nom UPAC, the name UPAC, the name that was given by International Union of Pure and Applied Chemistry is called salaric acid. So in the same way, when we start looking at nomenclature and all those things, we are going to write names of these molecules in their nom UPAC. We're going to write names that will be used like globally. Like some of you might give me ethyl alcohol. I will know that this is ethanol, but another person won't understand what ethyl alcohol is because maybe they might be using the rules that UPAC has stated, you see. So the idea is at the end of this lecture, you guys are supposed to be able to write names in the form usual, which are the normal names like ethyl alcohol, which is also known as ethanol. You can also say all those things. But the idea is, at the end of the day, you guys are supposed to be able to name molecules. When you're naming a molecule, there are principles, there are rules that you're supposed to apply. So like I say, if you're able to understand or retain all these rules, the nomenclature on Chimie Organic, all of them, if you understand them, like I say to my friends, if you understand them, then you can be a law student because there are a lot of rules that you're supposed to apply when you're naming compounds. Take, for instance, you have a compound that has got a carboxylic acid function. You've got an aldehyde, you've got a cetone, you've got an alcohol, you've got an alkene. How do you name it? So you are going to apply rules of nomenclature that states that the carboxylic acid is always the predominant function in organic chemistry. So whenever you have a compound that has got a carboxylic acid as the terminaison, it means that compound is automatically a carboxylic acid. Take, for instance, you've got amino acids. Amino acids have got what you call a carboxylic function, and they also have what you call an amine function. So now you're going to look at it, which one is dominant. So this is a table that I derived for you guys. The ones in red are what we're going to look at. The ones in black, we're not going to look at them because if I look at everything, you guys won't have time to learn about stoichiochemistry and nomenclature in stoichiochemistry. So the ones in red are what we're going to look at. Then this is the table you guys are going to be using for predominance. So it means if a compound has a carboxylic acid function, it means it's the most predominant function we're going to use when we're naming the molecule. So I'll go back to this example. So take, for instance, molecule B. If molecule B had the molecule B here has got what you call what is this? Carbon, and an oxygen atom here. So this nitrogen here shows that this is an amine. So there's an amine here substituent, and you have first carbon atom. So the first carbon atom always bonded to oxygen is called an aldehyde. So an aldehyde is a carbonyl group. So there are two functions on the aldehyde. There's what you call an aldehyde and a keton. A keton, that's in English. In French, it's called a ceton. This one. Sorry guys, I'm a bit fast. So like you guys are supposed to go for your break. So yeah, it's called a ceton. So the carbonyl functions are divided into two. It's what you call an aldehyde and a ceton. So for those that are going to be doing biochemistry, you're going to be using these two functions because they are a build-up for glucides, which are also known as carbohydrates. So like I said, if you're going to have a molecule that has a carboxylic function, it means that molecule is automatically going to be called a carboxylic acid. But if you have a molecule that has an aldehyde function, a ceton function, an alcohol function, it means you're supposed to look at this table and look at which one. This is like a reactivity table. You're going to look at which one is going to be the first one. So it means this one, the aldehyde, will be the first one. Then whatever follows behind becomes a substituent of that molecule. Then we're going to look at representations of molecules. Molecules can be represented in three main ways. You've got what we call representation de Cram, Newman, and Fisher. So with the representation of Cram, this is where I said at some point we're going to represent these molecules in 3 dimensions. So when you're representing a molecule in 3 dimensions, you are going to use what you call a wedge and dash. So the wedge is this one, and the dash is this other end, this side. So now you're representing the molecule in 3 dimensions, just like this here. Here. Now you'll be having molecules. Now you're supposed to represent them in this form. Like you have, take for instance, this is a carbon atom, and this is methane. So it means you're going to have carbon, hydrogen, kunuma. So if something is behind, we use dashes. If something is in front, we use the wedge. Then the other one is going to be in the plane. So for now, I don't expect you guys to understand because this is a topic we're going to look at in depth. Then we also have what you call representation de Cram. Now, no, the Newman. So Newman representation is now like you have a molecule. A molecule, take for instance, you have, I'll use a pen. I'll use a pen as an example. So the pen has got what you call the bow. That's the reason why it's called a ball pen. You have what you call a bow. This is why you guys press, and this is where the ink comes from. Now, with representation the Newman, or bien projection the Newman, we're now looking at the molecule. You're now looking at the molecule like you're looking at the pen from its bow. You're looking at the molecule like you can see here. Yeah, you can see here. You're looking at the molecule here. There's like a point here. Now you're looking at the molecule through this point. So we'll be representing molecules, how you can draw a molecule that's represented in this form. So the way a molecule is represented from the right perspective to the left perspective is different. You see? So when you're looking at the molecule from this side and looking at it from this side, it's different. So you have what you call the staggered formation. You have what you call the eclipsed formation. You have what you call the what's this? Décalé ou bien étoile. There are a lot of formations that we're going to look at with Newman projections. But for now, like I said, this is just a rappel of what we're going to do. Then we have the other one, which is called Fisher projections. Now, on Fisher projections, you guys that are going to be doing biochemistry, I'm emphasizing mostly on the guys that will be doing biochemistry because these are the things that you're going to be finding. So with Fisher projections, you're going to look at how you draw glucose molecules in Fisher type of orientation, because you'll be using these representations to form what you call cyclic glucose molecules. So you find that this is a Fisher projection of glucose. Now, when you go to the cyclic representation, you're supposed to understand that this carbon atom bonds to this carbon atom, then later on you have a cyclic structure. So with a Fisher projection, it's basically the same as the Formule plane Developpée, but now this time you're showing each carbon asymmetric that the molecule has. So when it comes to asymmetric molecules and all those things, this is now where we go to the principle of stoichiometry and isomery. So when you talk about isomery or bien stoichiometry, stereochemie. So you have isomers, which are molecules that have the same structure formula, but you have molecules that have got the same chemical formula, but they differ in the structure formula. So we've got to what we call isomer de plein or bien de constitution. So on these ones, we have what you call the squelette en fonction, en chaîne, or bien en position. So isomery de plein differs. There are those that are different in the form of the chain, some that are different in the form of a position of the function, some that differ in the function, some that differ in the way the structure is formed. Then we are going to also look into the principle of stereochemie. Now, this is where now organic chemistry becomes a bit like it needs you to think, but it's very easy. So stereochemistry or bien stereochemie is the study of molecules in 3 dimensions, X, O, Y, Z. So we have what we're going to do is the first part we're going to look at is stereoisomery deconformation. So we're going to have molecules like cyclohexane that can be twisted in whatever form that we want without breaking their bonds. So we've got what we call form baton, form chaise. So if you guys have seen that logo on the Facebook Messenger thingy, it looks something like this. It looks something like this. So this is what you call cyclohexane. So cyclohexane, when is twisted, cyclohexane, which looks like this. What is it? Cyclohexane that looks like this without this CH3. When twisted, that is now when you're talking about conformation, isomère de conformation. When twisted with different positions, it now forms this molecule here that you're seeing, this compound here that you're seeing. It now forms this thing here. This is what you call conformation en chaise. Oh, yeah, on chaise, because this looks like a chair. This looks like a chair. So this is cyclohexane, but now because it is a conformer isomer, it now forms a chair form. There's also what you call form baton. We're going to look at that. Then we're going to also look at isomery de configuration. So isomery de configuration, we're going to explain the principles of what you call enantiomers, their stereoisomers, epimers. Then at the end of it, we're going to explain the principle of chilarity. Then we're going to explain the importance of chilarity. So here's the question: is aspirin acetylsalicylic acid chiral or achiral? So at the end of the stereoisomer class, we're going to determine if aspirin is chiral or bien achiral. Then at the end of all the class for organic chemistry, we are going to at least laugh at this joke that I have here for you guys. So you guys understand that, I don't know if you understand or you've seen this meme before, but the idea here is you have two double bonds. in organic chemistry, when you have two double bonds, you no longer call it an like you guys would call it an alkane, but you call it a diene. Now a diene has two double bonds. This is where the di comes from. So the diene comes from the two double bonds. So if there are any questions, please ask them, because you guys are supposed to prepare yourself for the next class. So if you have any questions, please ask them right now. Then if you have any questions, please ask them right now, so that if I can answer before you guys go for your next class. But sorry for the speed, because I'm supposed to let you guys rest before going for another class. So if there are any questions, please ask them. Then on Tuesday, we start learning organic chemistry. So thank you very much for your attention and participation, for those that participated. If you still have questions on certain things that you did not understand, please, you can still inbox me. I can still explain further on certain things that you did not understand. Yeah. So if you have no questions, then on se verra, inshallah.
Daliso,
Yes, please.
are you going to send us the slides?
You want me to send you this slide?
Yes.
Okay, I'll send it.
Okay, thank you.
All right.
So we are not going to have Chimie general.
No, you guys will be having, those that are doing medicine will be having their Chimie general at 15.
All right.
Yeah. You're also supposed to attend Chimie general.
Oui.
Ah bon.
Apa kabar?